So we are going to continue our discussion about how we interpreted this things, how we interpreted mathematical theory of measurement, how observer and observed go into the making of quantum reality, which is the admixture of both measurement, observable, and observer in that sense. So in today's class, what we are going to see, how we can see the rules of measurement, rules of measurement, measurement, rules of measurement, and slash disturbance by measurement. So one is measurement, another is disturbance by measurement. So these are two things. So in that sense, in the probabilistic sense, if we want to measure, for example, if we have probabilities, if you have an, for example, measurement mv of an entity v and mw of an entity w. So the probabilities of these two events can be given as m ui vk, and this one it will be probability of vk wm. So so these are the measurements, measurement MW and MV of entity V and W. So you can say probability of obtaining omega m can be depends only on the value of Vk obtained. So this is the thing. So but it's independent of the value of Ui. So which means that so if an event precedes another event, so the thing is that an event happens and it's preceded or succeeded by event, and then it's followed by second event. So the event at the end, it will be oblivious of the starting event. So it's more conscious of the immediate events. So if you bifurcate events in terms of succession, and we are going to measure probabilities vis-a-vis that thing. So you can say probability of ui, vk, wm can be written as probability of vk this thing. You see, so you can say you can ignore the probability of this thing, the initial thing. You can just the end part of the observer may just only construe probability of these two things only. So if we have a general theorem of multiplication of probability, for example, so probability of ui, vk, wm is basically probability of ui, vk, probability of ui, vk, this thing. So it will be basically, you can say probability of ui, vk is, so you can ignore this one. It's basically probability of vk and this thing. So if we have, so this is in probability called the rule of elimination. So we are going to start we have to come to a point basically how this rule. So how, if you can eliminate one of the intermediate probabilities, as an elimination, so you can state it as the probability of u1 is basically v1, v2, v, so on and so on. So it's equivalent to sigma of k. So you can have this k can be is a repeated index. It's probability of ui vk, probability of vk omega n. So vk ui omega m. So we are this thing is denotes logical. This denotes or logical or this or this or this. So in the final scheme of things, you can eliminate some common things, repeated things. You can so such that it's probability of first event, and you can just think and omega m. So if you remember in the when we constructed those triangle diagram or quadrangle diagrams, in which we just related two on the operators acting in a given space, and then that operator acting on others, how could relate those states which are being operated upon by operators having different indices, and how can relate them. Operator acting on a given state, how can there is an interchangeability of two states which are being mediated by an operator. So there can be two or more states and many more operators. So there was a certain triangle diagram as well as a quadrilateral diagram where we can relate them. So you can have that understanding here also, that chi of k, if it's an event, so you can have it eta km zeta m. So you can write it like this. You can write it like this. So m is some repeated thing. You can see how this state can be related to this state via this thing, via this. It can be an operator or it can be a matrix also in that sense. So probability of an event in this consideration vk Wm can be related as eta km square. So these are the 1, 2, 3, 4, 5, 6. This is 7. This is 6. This can be 1, 2, 3, 4, 5, 6, 7. Now, but consequently, 4 can be written as. So you can see probability of this thing Vk Um. So this 4 means. So I'll write it. I'll write it 1, 2. This is 3. This is 4. The 4 can be written as like this. So you can see. So if there are, this is probability u1, and these are or different subsequent events which are to be measured, or subsequent states which are to be measured, and those states can be quantum mechanical states or classical states, since we are interested in quantum mechanical states which make some difference. So you can have this probability of ui and at the end it's omega m. So you can write it as omega ik square and eta km square. So omega ik and km. So it's this thing. So this is this thing. So in this mathematical, so if you remember, there is that triangle thing, the triangle in figure 11. The figure 11 is that 11. So it's a triangle thing. So if this is sigma, this is psi, this is tau. So this chi, this is omega, this is phi. So you can go from psi to tau, tau to psi, and back via this operator, which may be two cross two matrices in that sense. So you can see from this you can see that we can write phi phi q as, or we can write. So you can see we can write phi phi q is basically m vim zeta m q, and you can see probability of UIWM can be written as VIM square. This is K is common. You can see K is common. So you can write it as VIM square. And from this triangle, from this triangle sigma, tau, psi, or he has written rho. So it's not in the previous figure, it's omega phi. So we can replace it by sigma, rho, and tau. Sigma, rho, and tau. So VIM can be represented as IK eta Km. Now you can see here it's 2. So you can see probability of UI omega m is equal to if you have this square of this thing, so it will be square of IKM eta Km square. So we are coming to a contradiction. In one case, we might have ignored. It contradicts the relation 7. This contradicts the relation 7, where probability of the states or events initial and final. In one case, we might have ignored the common term, common indices. In the other case, we have not ignored it. So it leads to some sort of contradiction. So you can say that square of this is not equivalent to you cannot say that square is different is from the sum of squares. You can say it square of sum is different from the sum of squares. So this is a contradiction. So this contradiction means one way of resolving this contradiction in the language of probability is that if we just take recourse to the frequentistic interpretation of probability, that an event which is being observed is basically the probability of all the events, combined events which we have been observing it. The maximum number of times the event has been observed, it is the given frequency of that state which has been observed. But here the point is that that the contradiction was arrived at that we can ignore some sequences and we can have the states and the consecutive states. So the thing is that one way of resolving is that we have to just replace it by the tautological statement of so the probabilistic statements are tautological statements. They may be linguistic rules. So it doesn't. So if we ignore one of the things in the chain, common chain, only account for the end part of it. So it's basically how you are stating a logical problem rather than describing a physical state. So physical thing. So the logic of physical world, and if we adjust our logic to the description of the physical world, these are two different things. Maybe Reichenbach is just trying to allude to this logic of the world which we are constructing, or logic, or the world of logic which comes out from the observational part of those measurements. So these can be two events, and it might be the thing is that they can have wrong interpretations. So rather than ignoring a given intermediate state or event in the chain, it doesn't carry sense in that sense. So for that purpose, you can say that now we are coming to two sort of realities to see. The two realities are that probability of mu u I v m v v k is equal to, this is one, omega I k square. So this is so we're taking this and this, and in the new notation, this probability of m u u I m v v k. So it's probability of m v v k m u u I. Now what we can say from now on, we can say probability of MV, VK, MW, WM is basically neta Km square. So this is V is goes to this, K goes to this. So we have ignored this event, maybe this. And this one, so this is one probability square of the probabilities. The other is the this one. So this one can be represented by this, where things have not been ignored, or here probability of mu ui mv mw m omega m is equal to sigma k omega I k square neta km square. So you can say it like this, km square, or probability of mu ui m omega m is equal to sigma k omega k neta km square. So you can say it like this. You can say it like this. So you can see it from this. We can say that instead of contradiction, we can simply derive the inequality. The inequality is that. So we can just one way of resolving this frequentistic interpretation of probability. We can say that we can resolve this contradiction of probability of mu ui mv mw. So if you have two events, it's not equivalent to one ui mw. So in this case we have ui mw. So we have here we have ignored, and v is ignored here. So here you can say that so one is the logical way of stating the things, that we can ignore the sequence of measurement of events by only taking the last one, last state and its preceding state, or the first state and the end state. So you can ignore the these things in a logical interpretation of probability. But in the other way of interpreting is that we cannot, these are two separate measurements in that sense. They are two separate class of measurements in those things. And they need not necessarily be equal. So the question is, what has it to do with our so it has definitely to do something to our how we just are going to interpret things, because in whether it's in classical mechanics or quantum mechanics, we have observables, we have measurements of two or more observables or parameters or conjugate parameters, more precisely, if you use in the quantum mechanical sense. So, or we have a simultaneous measurement, we say there. When we talk of simultaneous, so in that simultaneous measurement becomes so how we are going to measure two simultaneous events. Or if it is not possible, what does it mean? So we'll come to that. If it doesn't mean, does it have to do something that we are measuring probabilities at different times, or that's it. So we'll see. So the influence of the measurement is even more apparent if we choose a third entity, W. So such that so it becomes more apparent if you use third entity, such that probability of mu ui mu is equal to delta im. So we are using this and this. So you can say we have these are repeated. If we are using repeated things or probability of mu ui mv mu um can be written as ik square and km square. So from this you can see again this probability of mu ui mv mu um is not equivalent to probability of mu ui mu um. So this is the thing. Now what you are going to see is that we can have so this book has used a very, or Reichenbach has used a very contrived, I would say, contrived argumentation to come up to how the uncertainty, to our understanding of uncertainty principle, that the measurement affects the even very definition of measurement should affect what is going to be measured, or measurement disturbs measured in its very definition. So how does it come out? He comes out it like this from this argumentation that so we can have two relations. One is this probability of S m v k w omega m can be written as m p v k mw probability of mu ui mv vk mw. So we can have all sequence of all events here. We have not ignored in this sense, we ignore some of them. mv vk mw. So if they are, for example, they are not equal, they are inequalities. Inequalities will lead to they are not equal, they are inequalities basically, these measurement of probabilities. So we can say that we can also restate these statements that For example, if we are going to measure an event or observable, so uh, an measurement will lead to uh, some succeeding observable is going to be measured. And so you can say probability of, you can say formulation is that a measurement which disturbs the object, but in which strict prediction of the result of measurement is. So even though measurement will disturb the object, but we can predict the disturbance or measurement of that disturbance. So such a world can be constructed in which mu, ui, mv, vk. So it's delta I plus 1 into k. So you can, so an event and measurement which disturbs something, it's going to have effect on some subsequent state, which can be written as this, such that if there are two switch states, if if we put mu for mv and uk for vk, and if an entity is measured entity is repeated, then probability of mu, ui, mv, mw, wm is basically equal to probability of mu, ui, mv, vk. So since we have replaced mv by uk, so we can write it as this: mv, vk, mv, wm. Or you can say delta ki plus 1 into k into delta k plus 1 into m. Or you can say delta k plus 2 into m. So we can, since we have replaced u by v, so we can, so this is a disturbance, and the disturbance, more disturbance, subsequent disturbances, they are two disturbances. So any consecutive disturbance will have we can measure which has effect on that thing, and a subsequent will have. So you can say so continuous measurements or continuous disturbance, and it will have the sequence can be accounted for accordingly in the progression. So now, what has it to do with uncertainty principle? So if we are going to write it like this: probability of mu, ui, mw, wm can be written as delta I plus 1 into m. So this result shows as before in the equality 18, as in the equality 18, 18 is this, which was this. This was our equality. Our equality was basically probability of m, u, ui, mv, mw. So in which one of we have ignored one of the sequences is not equivalent to this. So one way of resolving that contradiction was like this: that they are two separate measurements. Logically, we can say that we need not the intermediate measurements. We are only interested in the first and the last one. So we can, repeated measurements can be ignored. So that contradiction was said that they are basically, these two measurements are two separate measurements basically. So we are basically coming to the same thing. We are coming to what I should say, the end part of it is that disturbance of object by measurement shows that result of measure can be strictly predicted by this understanding. Although even though this cannot be, for example, this equation cannot be strictly valid in quantum mechanics, because if an if a measurement on an observable, it will affect measurement in an incontrovertible ways that we cannot quantify things in the exact classical sense. So this, but we can use this formula for proving that interdeterminacy is not a logical consequence of the disturbance. So here it's a very important point. So interdeterminacy is not logical uh, consequence of disturbance of object. It's rather the reverse case. It's rather the reverse case uh, which holds. If there were no measurement, if there were no disturbance by measurement, we could make strict predictions. We could make strict predictions. The way we do in classical mechanics, strict predictions can be made if there are not disturbances. If there are not disturbances by measurement, we can make strict predictions. The way we do in classical mechanics. But the question is, interdeterminacy is not a logical consequence of the disturbance of the object. So we'll come to the other point. It is the reverse case which holds. If there were no disturbance, if there were no disturbance by measurement, we could make strict predictions. That's fine. If there were no, we could make. So we have written it. Reversing the implication by negating the implicate. So if we just reverse this, or invert this statement, or reversing the implication of the statement, what does it mean? We come to the result that principle of uncertainty implies a. So what does it? So this is an important point. Principle of uncertainty implies disturbance of object by the so this is a very important thing. So what this is how Reichenbach states it. So there's an inverted way of saying it. So it's in the very assumptions of quantum mechanics that what I should say, object is disturbed in the process of measurement. So it has a very this thing has very. So on the epistemology of how we construct quantum mechanical reality. So in the classical relativity, so at the end what we have arrived at is that we don't assume that measurement is going to get affected by the measured in an incontrovertible way. We can account for that. So it's in the postulational thing, that postulational thing we arrived at through contrived reasoning. Reasoning was that probabilities, the frequentistic interpretation of probabilities. So in which case we can ignore the intermediate events. We can take the events, these two interpretation of probabilities. We can do away with them, that those two interpretation, whether we can ignore a given measurement of probability. By saying that there are two different interpretations, there are two different inequalities. So logically, we can do away with this. And from this, we could arrive at it and in an inverted way. So what Reichenbach wants to say is, or what we an interpretation of quantum mechanics is, that it's in the very assumption of quantum mechanics that measured is going to be affected by the measurement. So that's in the assumption of quantum mechanics, which we have arrived at it. So it has very important implications for how we can construe this understanding the quantum mechanical reality in the general sense, in the epistemic sense, and also in the sense of whether the duality of observed and observed, it's somewhat ingrained in the existence of in the existence. Yes, the duality is ingrained in existence or ontology or in being. That's it. In some fundamental level. So stop.